Thank you so much for watching our last video on the numbers theory, where we apply Bezout's identity from Euclid's algorithm to solve a particular simple equation. And of course, I want to explain that the equation of that time that we had ax plus by is equal to c is called a Diophantine equation. A Diophantine equation. So equation of this type can be solved using Bezout's identity to find x and y. And of course, in that example, we are looking at 16x minus 28y is equals to 4. But suppose this is, let me say we have this equals to 8. We can still solve it using that. Remember when we use Euclid's algorithm, then the reverse of Euclid's algorithm gave us the Bezout's identity. We actually found that x is equals to 2 and that y is equals to 1. If you plug this in, it will not give us this, but if we multiply 2 out through, we can have actually 8. So that's what we learned in our last class, how to solve differential equations using Euclid's algorithm and Bezout's identity. Now today we want to expand what we learned last time to solving of linear congruence, because the congruence equation is actually another form of the differential equation. Now, what is the linear congruence? Of course, from the word linear, you've seen that the power of the variable x in this case will just be 1. So a linear congruence is a mathematical statement of the form ax is congruent to b in mode y. Mode is a short form of the word modulus, which means the remainder of b when we divide a number by m. We are not interested in the quotient at this time. We are actually interested with the remainder after division. That's what modulus is all about. So linear congruence is the mathematical statement of the form ax is congruent to b mod m, where a, b, and m are integers. Now the letter z is a symbol for integers. Of course, that's not z. It takes the form of a symbol that is a short form of the German word Zahlen, which actually means numbers. So with this, we can solve some problems of this form. But how can we solve such problems? One way is to identify the fact that if the GCD of A and M cannot divide B, then that question does not have a solution. Let's take an example of such a problem. And let's see you have 3x is congruent to 5 in mode 6. Now you know that the GCD of 3 and 6 will be 3. When I say GCD, I'm referring to the HCF. And then 3 cannot divide 5. And so this cannot have a solution. Now, if the GCD of A and M is 1, and then it automatically means that you can have um, an infinite number of solutions. But there are some cases that we can have particular number of solutions in which we are going to look at. In that case, we look at particular solution, and then we now look at many other solutions. There is something else I need to actually explain here. That for us to have solutions to linear congruence, we need to find out how many solutions can we have. I want to explain that again. Suppose we have a congruence, let me say 16 um, is congruent to, let me say 4, let me say in mode 10. Now we observe that 16 and 10 have a GCD of 2. Now, and 2 divides 4 two times. So it simply means that since it divides these two times, we are going to have two incongruent solutions, of which the residue class in that case, when I say residue class, I'm referring to numbers that can make up to 10. That is from 0, 1, 2, 3, 4, 9. Now, if you plug in any of those numbers, the value can never be, the residue class will not be above 10, just from 0 to 9. And so we are going to have two incongruent solutions that can actually be gotten from the residue class. So this will have a solution, but you will have two incongruent solutions. So let's solve other problems. Let's go to examples in solving problems in linear congruence. Let's take a problem, number one. We should solve the congruence. 2x is congruent to 1 in mode 3. Now, there are many ways to solve this problem, but I want to mention just three ways of solving this problem. One of the first ways you can solve this problem is to find out what can x be. That is to say, if x is a number, what number can it be that if I multiply it by 2 and divide by 3, I will have a remainder of 1. So let's look at those numbers, the possibility of having them. Now, in the textbook for high school in most countries around the world, what students are taught is to create the Callis table, a table of multiplication and addition. Let's take, for instance, if you have a table like this. So supposing you have this, you have the numbers 0, 1, 2, 3. Then you have the same this way. Let me say um, we have also have, let me keep it here. So can you go down? No. So we have 0, 1, 2, 3. Then you have 0, 1, 2, 3. Then 0 times 0, this is, let me say, this is in mode 3. 0, 0 will be 0, 0 times 1, 0, 0, 0. Let me use 1. 1 times 0 is 0, 1 times 1 is 1, 1 times 2 is 2, 1 times 3 must be divided by 0 by 3 first, since we are working with those 3, and that will give us a remainder of 0. Then 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4. 4 divided by 3 will have a remainder 1. 2, 2 times 3 is 6. 6 divided by 3 will give us no remainder. Then 3 times 0 is 0. 3 times 1 is 3. 3 divided by 3 will have us remainder 0. Then 3 times 2 is 6. 6 will give us remainder 0. 3 times 3 will give us the same thing. So what we can see here is that when we are working with 2 and 2, we have 1 as a remainder. So automatically, the multiplicative inverse of these 2, which is x in this case, is 2. And actually, you can only multiply 2 by 2 and divide by 3 to have a remainder of 1. So using that table in front of us, we can write in our solution that 2 times the inverse of 2, then here we'll still also multiply the inverse of 2, inverse of 2 by 1 in mode 3 is going to give us a solution. So automatically what we mean is that x is congruent to 2 in mode 3. So because 2, the inverse of 2 in this case is also 2. And the solution is that the x we have here is congruent to 2 mod 3. And that becomes our solution for this type of question. But apart from solving it that way, we can just use mentally and tell ourselves that if we multiply 2 by 2, we are going to divide by 3 and have remainder of 1. And that becomes our solution. Let's take another example. Let's take example 2. Supposing we have a number like 3x is congruent to 4 in mode 7. So like in the previous case, the table may be larger than the previous case. And we may not want to waste a long time in doing that. So we need to ask ourselves, what can we multiply by 3 and then divide by 7 to have a remainder of 1? We plug in the numbers 3, that will give us 9. 9 divided by 7, we have remainder 2. We plug in 4 here, that will give us 12. 12 divided by 7 will give us remainder 5. But if you plug in a number like 5, so if x is equal to 5, we are not actually writing the modulo yet. So 5 times 3 will give us 15. 15 divided by 7 will give us remainder 1. So we multiply 5 on both sides. Here we are going to have the inverse of 5. So we are going to have 3x times 5. Um, that will give us 4 also times 5 in mode 7. And that you know that this we are referring to the inverse of 3, that is this 5 now. So we have here that because 5 times 3 is actually 15. 15 divided by 7 will give us remainder 1. So that one here doesn't change anything. So we have x is congruent to 20 in mode 7. In mode 7. Now let's see. If we divide 20 by 7, what's the remainder? The remainder is 6, which actually implies that the original congruence we were given 3x is congruent to 4 in mode 7 will now become x is congruent to 6 in mode 7. So actually the value of x was 5, and then here we are, but in mode 7 we have the x is congruent to 6 in mode 7. We have many other examples that we can solve using this method, or we can even convert it to Diophantine equation and then use Euclid's algorithm, B2 identity, and solve it, or any other method. But for now, let us stop here so that we can have more videos for us to learn, and then you can meditate on this, solve more problems, and then wait for another video. But do not forget to hit the notification button. Do not forget to subscribe. Do not forget to like and share this video so that others can learn from it. Thank you so much.